Hello, Matthews Gatos here. In this video, I'm going to cover horizontal and vertical reflections. So let's get started. A reflection is a special type of a transformation in which each point in a function is reflected in a line of reflection. Now, after I've done my reflection, the image and the original points are the same distance from that line of reflection. So reflections change the orientation of the graph and by process of elimination, the position, but it does not change the shape of the graph. So in this video, we're covering vertical and horizontal reflections, and that is going to be based on the parameters of A and B. We're going to look at three reflections in this course, reflections in three different lines. The first one is the x-axis, y equal to 0. That's a vertical reflection. The second is the y-axis. That is the line x equal to 0, which is a horizontal line of reflection. And the last one is the diagonal identity line, y equal to x. That's for inverses, but we'll deal with that a little later. Invariant points, reflections can have invariant points, and those are points that will stay the same after a transformation. So we just did a video on translations. Why didn't I mention invariant points there? Well, let's look at this graph to begin. So as an example, if I were to do any translation, let's say I pick it up and move it right, you can see all my points are moving. If I move down, still all the points are moving. Nothing stays the same. In fact, translations are the only transformation without invariant points because all the points move. When we describe reflections, same as before, except this time it's only two steps. The first step is what it is, which is a vertical or horizontal reflection. Then where it is. It's either in the x-axis or in the y-axis. When we do reflections, we reflect in the axis. So describing what it is and where it is. Let's talk about vertical reflections. So vertical reflections are tied to the parameter A on the outside of f of x. If A is greater than 0, making it positive, there's no vertical reflection. If A is less than 0, making it negative, there's a vertical reflection in the x-axis. Because it is vertical, it only affects my y-coordinates. So anything y that is above the x-axis where it's positive, after the reflection will be below the x-axis where it's negative, and vice versa. In terms of my mapping notation, xy becomes x negative y. Notice that my x values stay the same. It is only my y values that change. Now, this does not mean y becomes negative y. What it actually means is that this y, whatever its value is multiplied by -1 to give this. So if y started out as positive, when I multiply by -1, it ends up negative. If y started as negative, when I multiply it by -1, it will become +1. Let's look at an example. So here we have f of x, the original above, and g of x, the image below the x-axis. I can clearly see that the points all line up vertically, which means I have a vertical reflection. So let's describe it. What it is, vertical reflection. Where it is, in the x-axis. So this is a vertical reflection in the x-axis. Does it have any invariant points? Were there any points that did not change? And I can see this point right here stayed the same. Any point, in fact, on the line of reflection, in this example, the x-axis, will be invariant. So x-intercepts are invariant for vertical reflections. So the point 0, 0 is invariant. Let's talk mapping notation. So I can see because the points line up vertically, my x values stay the same, but my y values go from positive down to being negative. And I do that by multiplying all of them by -1. So my mapping notation is xy becomes x negative y. So since x stays the same, my equation would be g of x equals -y. Well, you can see here, y is f of x. So I do -y, which would be -1 multiplied by f of x. So my function is g of x is negative f of x. A negative on the outside tells me there is a vertical reflection. Let's look at horizontal. So horizontal reflections are based on the parameter b on the inside by x. So if b is positive, no reflection. If b is negative, there is a horizontal reflection in the y-axis. Now, b only affects the x-coordinate. When I reflect horizontally, only x change. So when I have x to the right of the y-axis where they're positive, after a reflection, they will be to the left of the y-axis where x is negative, and vice versa. Our mapping notation is x, y becomes negative xy. So notice my y values stay the same. It is my x values that change. Again, x going to negative x does not mean x is negative. It means x is multiplied by -1. So if I take x and multiply it by -1, I get negative x. So if x is positive, multiplying it by -1 makes it negative. If x is negative, multiplying it by -1 makes it positive. Let's look at an example. So in this one here, I have f of x and g of x. I can see that these points here line up horizontally, which tells me this is a reflection. So to describe this transformation, I know that what it is a horizontal reflection. Where it is in the y-axis. So are there any points that are staying the same, invariant points? Invariant points are any point that does not change, and I can see a point right here that stayed the same. So I have an invariant point on the line of reflection, which in this case is the y-axis. So invariant points would be the y-intercepts because they are on the y-axis. So in this particular example, the invariant point is 0 and 9. In terms of the mapping notation, let's look at what happens. So I can see that all of my y values are lining up. They're staying the same. What is changing is the x values. They are going from negative to be positive. To go from negative to positive, I am multiplying by -1. So -1 times x. There is my mapping notation. In terms of the function g of x is going to be all of the points on f where the x values are multiplied by -1. So g of x is negative x. Let's try an example where we put it together in terms of graphing. So now I'm given a graph of f of x, and I want to graph y equals negative f of x and y equals f of negative x. So for this one here, negative f of x, the negative on the outside tells me I have a vertical reflection. So that means my points line up vertically. X stays the same, only y is changing. So when x is -4, y is going to go from -3 to +3. When x is -2, y goes from -3 to +3. When x is 0, y goes from -1 to +1. When x is 1, that stays the same because it's an x-intercept. When x is 3, the y value goes from 4 to -4. When x is 4, y is 0, so it stays where it is. When x is 5, y goes from -4 to +4. So I'm going to take that and put it up at +4. So now all I have to do is connect the dots, and that's the graph of negative f of x. If I look over here, graphing f of negative x, the negative on the inside means horizontal reflection. That's in the y-axis. So my points are going to line up horizontally. That means that the y is going to stay the same. The x value will change. So when y is -3, this x value of -4 is reflected to be +4. Also, when y is -3, the x value of -2 is reflected to be +2. Here, when y is 0, it stays where it is, invariant point on the y-axis. When y is 0, the x value of 1 reflects to be -1, and the value of 4 reflects to be -4. When I have an x value of 4, a y value of 4, the x value of 3 reflects to be negative 3, and I think I forgot one down here. When y is negative 4, the x value of 5 reflects to be negative 5. And I connect the dots, and that is my graph of f of negative x. In my last example, I want to look at an equation. So I have this function, the cubic function, f of x is this cubic function, and I want us to write the new equation in terms of x and in terms of f of x after a reflection in the x and the y axis. So both is happening. So to reflect in the x-axis, that's a vertical reflection, so you can see why y is changing. To reflect in the y-axis, that's horizontal, which is why x is changing. Now, when I want to write it in terms of f of x, this is general to any function. So I'm looking at, in general to any function, how do I show it's reflected in x and y? So if I start with any function f of x, to reflect in both, I replace y with negative y and x with negative x. Now I don't want a negative y equals equation, I want a y equals equation, so I divide both sides by negative 1. So negative y divided by negative 1 is positive y. And then f of negative x divided by 1. There's really an imaginary 1 in front here. So it's like doing 1 divided by negative 1, which is negative 1 times f of negative x. So my equation in general will just be negative f of negative x. Now to write it in terms of x, this isn't in general. This is specific to only one function. In this case, it will be specific to the cubic function. So our cubic function is y equals negative x cubed plus 2x squared plus 7. So to reflect it in both, I replace y with negative y and x with negative x. Really important for your x values that you do that inside the brackets. So I have negative y equals. Now, negative x cubed is negative x cubed. Times by negative 1 is positive x cubed. Negative x squared is positive times 2, and 7 did not change. Now to get y by itself, I divide everything to be fair by negative 1. So I get negative y divided by negative 1 is positive y. Negative x cubed minus 2x squared minus 7. So that's in general form in terms of f of x, and specific form in terms of one specific value. So that's reflections in graphs, equations, mapping notations, and descriptions. Perhaps one of the most interesting reflections is the reflection of pi. Did you ever notice when you have pi 3.14 and you reflect it horizontally, you end up also with pi? Coincidence? I don't think so. I hope this video helped. If it did, please give me a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and we'll see you for the next one.